Hi there, I'm Richard Rahn, and welcome back to part 4 of this series, Creating the Perfect Value Stream. And if you haven't seen parts 1, 2, or 3, you can click on the link on this page and go back and view those. So I've been trying to keep these videos down to 10 minutes. I think I went over on the last one, but I know how discouraging it is when you see a video you might be interested in, but then you find out it's like an hour long and it becomes impossible. So we're trying to keep these short, but fortunately you'll be able to read a little more detail in the text below on this video as well, to supplement what I'm not saying in this video to keep it short. So here's the deal on this one. We have our line design, our value stream design, and we went through the basic steps of how to do that in the previous part 3. But now we need to talk about some quote-unquote advanced topics, things that you really need to pay attention to that could make the difference between a well-performing line and a super-performing line. So there are 5 aspects that really need to be considered. I'm sure there are a lot more than 5, but these are 5 big ones that you need to keep in mind as you go forward. So step 1, I'm calling it hurdle 1, before you fire up CAD. So part of the process, obviously, of design, just like designing a house, would be to end up with a set of drawings. Now, if you're building your dream house, and you've got an architect with a great 3D modeling or 3D CAD system, then he or she may be able to take you on a virtual tour, walk you through the rooms on a computer monitor and give you an idea of what it's going to look and feel like. And potentially you could come up with some improvements based on doing that. Well, let's do something similar in our mixed model value stream. So we need to really have a model. And the reason for that is really critical. There are a lot of moving parts. This is like a Swiss watch. There are a lot of gears that are connecting and a lot of variability that's inherent in this kind of model. And it's virtually impossible, let's admit it, to understand how all these things are going to interact just in our mind. No matter how smart we are, there are just too many moving pieces and too many potential scenarios, changes. For example, we could have different products on any given day, different products, and a different mix of those products and different quantities. And those products have different work content times. And people work faster or slower. Human beings are just human beings, right? They're inherently kind of variable in their work speed. So there are all kinds of reasons why we're not going to really be able to understand with total clarity how this line is going to perform without having some help. Now, some decades ago, we didn't have any help. You would have had to just build the line and then test it in the real world and make adjustments. We don't want to do that, though, because that's the most expensive time to make changes, is when it's already in place. Right? It's already almost too late. It's going to be very expensive to change things. So fortunately, we have a technology available to us called simulation modeling. And we could spend days talking about this, but the concept is real simple. There's software available to build a model of your line and then run experiments, basically. Try this mix of products, try that. And what you're trying to confirm is 2 basic things. You want to make sure you get the volume, right, or the throughput that you need to meet customer demand. That's pretty critically important. And the other thing is you don't want to do that inefficiently. So you're looking at the resources that you're applying. That's people and machines, workstations. You want to look at the resource utilization and get it up to a high level. So the simulation model allows you, it doesn't necessarily tell you the right answer, but it allows you to run experiments very quickly in simulation time, which is a fraction of real time, right? Fraction of human time. So how do we do this? Well, if you have that expertise in your company, great. If you don't, there are dozens of simulation software packages available, some specific to manufacturing. And there are lots of people that are available out there in the world to help you do that. Don't recommend just buying software and trying to learn it unless you're a super genius at this stuff, because the learning curve is pretty steep. I've had firsthand experience working for a simulation company, so I know and appreciate what it takes to really ask the right questions and really drill down deep and really build a model that reflects reality. So it's not a simple task, but there's no problem with access to the software or resources to help you do that. So really suggest, unless your line is very simple, suggest considering investing in that. So that's hurdle number 1. So you have that available and you run tests. Hurdle number 2, formalize sequencing rules. So the order of production is really important. It's not simply based on first in, first out, or based on your customer due dates. You really need to understand how the mix of products impacts the line. I'll just give you a simple example. You may have an option process that's not designed at 100% of the line. So if you build one product after another that require that option, you're going to overload that feeder process. And you don't want to do that. So you might have a sequencing rule that says, never run 2 Model X's back to back, because you know that's going to overload that particular feeder line. In general, the most basic sequencing rule is try to mix high and low work content products, because if you build too many high work content or harder products back to back, then the line basically downstream is going to start drying up, the line upstream is going to be blocked, and your line performance is going to be impacted negatively. So building your set of sequencing rules for use by production control. So when you create a lineup or a production schedule, they're applying those sequencing rules and using them. It's critically important to line performance. And again, a simulation model helps you test this, because you can try different scenarios and see what works well, see what gives you the better throughput. But you need to have those ready. Okay, hurdle number 3, in-process Kanban. So we touched on this earlier. So we're talking about buffers here. Now, some lean aficionados, lean specialists regard buffers as a form of waste, right? I'm just adding more inventory to the system. But in a mixed model line where variability is inherent to the line, you're never going to get rid of it. You're never going to level load a mixed model line in the way that you would like. Then buffers become a critical performance enhancing tool. So where and how many is unfortunately, it needs to be determined through use or through experimentation, or just a rule of thumb, because there's no formula that tells you exactly how many buffers to overcome normal variability of work time and work content. So again, I'm sounding like a broken record here, but simulation modeling is a great way to experiment with buffers. And typically you'll find that the law of diminishing returns kicks in really quickly. In other words, more is not better. As you add more inventory to the line, system will degrade, or improvement will stop. But a few can help tremendously in improving throughput by allowing workers to continue working without stopping, especially in environments like lean environments where we're trying to build products one at a time, single piece flow. Then buffers become really critically important. So use simulation modeling to experiment and come up with an IPK strategy. Okay, so hurdle number 4. This is the most underappreciated improvement or method in the world of lean or in the world of manufacturing generally. So here's the issue. If you're trying to build products one at a time, so workers are not allowed to build WIP, basically, just keep on working and pile it up, and you have variability in that flow, then there are going to be times when the worker either can't move the product forward, or they have nothing to work on, right? They have nothing coming to them. And in either case, that worker is waiting for something to change. Now, if that person can move to another place in the line based on rules and based on a disciplined kind of movement and not simply wandering around looking for something to do, then that person can add value, right, at another place, at another station. And of course, then productivity will improve rather than be degraded. So we call that flexing. Flexible workforce. People are flexible and able to work in more than one station. And that's the goal. So how much improvement could we expect? Well, there's a book I'm recommending to you called The Basics of Self-Balancing Processes by Gordon Garan. And he reports, based on projects he's worked on, 30% or more productivity gain. Of course, it depends on your situation today and the level of variability. Now, why isn't this more widespread? The reason is this technique implies 2 things. One, that you're over-designing the line. You're adding resources or workstations that are not always occupied, and that seems like a waste, right? Having resources or space and stations that you don't need based on current demand seems like a waste. Or understaffing the line where you have workstations that are not occupied because you have fewer people than you have stations. That seems counterintuitive for conventional thinking. But if you can appreciate how this would work, and again, you can experiment with your simulation model, what you're going to see is potentially a huge jump in productivity. And the main reason why this is so critical for a mixed model environment is that variability that causes those delays is inevitable. You can't get rid of it because you're going to have different products with different work content, etc. So this is certainly worth looking into, and Gordon Goran's book is really great. Okay, last hurdle is spreading the word. So the first line of defense for running the line and implementing it and maintaining it and improving it is going to be a level of people that are maybe not on your team, on your design team, but they need to be included in terms of knowing what to do and training. And Toyota, by the way, spends a lot of time on this in their company. Huge amount of investment in this level in your organization, which are team leaders and supervisors. So in a lean environment, the team leader or supervisor are responsible for a couple things. Number one, they're responsible for training new people. Number two, they're responsible for auditing to make sure people are adhering to standard work, to these flexing rules that we just talked about, to the use of material delivery techniques like Kanban. So auditing the system. And the third thing is continuous improvement. So soliciting ideas from the operators and then implementing those ideas, helping them get implemented. Usually small ideas that can be done quickly in the area. And typically a team leader would also be a first responder for any time that the andon cord gets pulled or the line is stopped or there's an issue of some kind, that team leader would be the first person to respond. Okay, so I think I've stuck to that 10 minutes. I hope maybe over a minute or two. So come back for part 5 where I'll talk about how to actually get started, how to learn this stuff in a structured kind of way. Some practical recommendations on how to get going, because there's a lot to know. Clearly, I'm just touching on these main topics, and really there's a lifetime of learning ahead of you, but we'll talk about how to get started with that. So see you next time. Bye now.